All right. Hey everybody, welcome to the Super Office Hours. So let's just wait a minute to see if the stream is up and running. We're live. Okay. So in the Super Office Hour, I'm gonna demonstrate how to do this practice midterm I've uploaded, and then some assignment questions. Gauss's law, which is what the current assignment is how do I put it? It's real easy to use if you get the basics, but it's like driving a car, which is to say there's a lot of things to keep in mind while you're doing it. And once you've mastered each of those things, it's straightforward, but learning to drive can take a little bit of time. So this week's assignment is full of little ideas put in together in new and different ways to help you get through it all, but it's a little bit on the difficult side. I mean, yeah. For some reason, I couldn't really find questions on this assignment that really kind of pulled its punches with you. I'm not sure what happened. I mean, this textbook was designed for Harvard students, and I don't know what it is about Harvard students assuming that they can do all these complicated geometry things, but yeah, so just give yourself some time. You can figure it out. It's not too difficult, but it is difficult, so grit your teeth. You can do it. It's all in the midterm. And also, before you get too depressed about that, you know, how should I put it? The midterm is bound to have all sorts of complicated and difficult questions on it, but maybe not as difficult and complicated as on the assignment, because on the assignment, you have, you know, hours and hours and hours to get through it. Whereas the midterm, you have 90 minutes. So I'm probably not going to throw you any real crazy curveballs like there are on the assignment. Also, please note that I've uploaded a list of topics for the midterm. Talk to any second-year student, and you will recognize that everybody has to learn this stuff. I'm not being particularly mean to you. And if you use that practice book, the list of topics is kind of a checklist to narrow down the content from the book, I think it'll make it a little bit easier. Very little on the midterm isn't going to be... You've had an assignment on almost everything on the midterm. The only different thing is electric potentials, and using electric potentials to find the electric potential energy, and using the electric potential energy to talk about the motion of your object. So it's, aside from that, you've seen everything on an assignment. All right. So before we go on, I want you to note something about test taking strategy. During these midterms, we tell you how much each thing is worth. This is worth 3. This is worth 6. This is worth 6. So the first section is worth 9 points overall, and the second and third are worth 6 points overall, which means that you have to do some combination of them too. You have to get some things right to pass. Okay, so test taking strategy wise, it's always wise to pre-read your midterm. So before you start writing anything, go through and read all the questions. I'm not going to do it because I wrote the midterm, so I know the questions on it. But you should look through the midterm before you start working on it, so you know which things are going to take more time and which things are going to take less time, and you know, account for it thusly. So what should you do? Maybe I should have put this midterm at the end and done all the questions first, because I don't really want you guys to try watching me do these midterm questions before you've tried it yourself. There is a thread in the human spirit to want to watch somebody else do something before you try it yourself. But really the best way to learn something and then go seek help once you have a better sense of what you do and don't know. So if you just watch somebody else do it, or if you just read the answers before you do anything, that will give you the sense that you know what's going on, but you actually won't have explored all of the all of the different possibilities for misunderstanding in your own head. And so, yeah, I mean, try doing it yourself. Try doing it yourself first, and then do it. So I'm not sure how long it's going to take me to work through this midterm. On the one hand, I can do all the questions because I wrote it, but on the other hand, I'm explaining it to you. Anyway, so that said, I mean, if you're following good advice, then you'll do well in life. If you're not following good advice, then you're taking a gamble. And who knows, maybe you'll win. I'm not one to say. So, but you should listen to my good advice, or somebody's good advice. Let's start these questions. A pebble with mass blah is hovering in midair. Oh, look, there it is, hovering in midair. You know that there's some electric charge on the pebble, and there's an electric field, blah, pointing downwards at its current location. What must the charge on the pebble be? Okay, so it's hovering in midair. What does that mean? It means its acceleration has to be 0, and that means the net force has to be 0, so that means there needs to be at least one more force on it. And surely we can imagine what these forces are. There's gravity pointing down. I can calculate exactly how strong gravity is too. 0.04 times 9.81. So gravity is 0 I hat minus 0.392 newtons J hat. There also has to be a force from the electric field. And so I know that because these two have to cancel out, the force from the electric field has to be equal and opposite to the force of gravity. So the force from the electric field is 0 I hat plus 0.392 J hat. But I also know that this is related to the amount of charge and the strength of the electric field, which I also know. Okay? And so the deal is, okay, 0 is equal to 0, fine. This is equal to this times this. 0.392 is equal to 2q, times 2.0 times 10 to the minus 5. And so q is equal to, just solve this algebraically, 0.392 divided by minus 2.0 e minus 5. There is minus 19600 coulombs of charge, which is a lot, but this is the type of answer you get when you write a question at 10 o'clock at night without checking your numbers. Anyway, that's what the numbers tell us. That's the charge on it. Next question. Okay, so these questions are all short answer, and that means that you probably shouldn't spend more than 5 minutes on them. I expect them to be fairly clippy. Sometimes they're multiple choice. Sometimes they say, draw a little picture. Sometimes they're, just a short answer like the last one. A negatively charged test particle is located at location A, right there. All right, so it's negatively charged. It starts out at rest. Describe the direction it will move. Okay. So it's going to feel a force from the electric field, but the complicated bit here is that I haven't drawn the electric field. I've drawn equipotential surfaces. So what do I know about the electric field? Well, the electric field, I'm drawing it red. The electric field is perpendicular to these surfaces, whatever it is. So the electric field is probably pointing to the right, or it's pointing to the left. Which one is it? Is it pointing to the left or is it pointing to the right? Let's see, the electric field points in the direction a positive charge feels a force, right? So as a positive charge feels a force, if a positive charge were to move in the direction of the force, the positive charge, right here, positive charge, E is in the direction, positive charge feels the force. So if it moves in that direction, it speeds up. So delta U has to, so delta KE is increasing, so delta U has to decrease, and so delta V has got to decrease. So electric field lines point in the direction of decreasing V. So the electric field lines must be pointed this way. Alternatively, I told you in class which direction, what the relationship here was. And so from an argument we talked about in class, a positive charge is going to feel a force to the left, and so a negative charge, wait, hold on. Electric fields point in the direction of decreasing V. I have this backwards. Decreasing V is that way. So that's the direction of the electric field. And this is a negatively charged particle. Careful. So it feels a force in the opposite direction. So it moves to the left because it's the opposite direction to the direction of the electric field, and or in direction of increasing V. Negative particle moves to the left. Okay. So by explaining my answer, what do I mean here? See all this? That's me trying to suss out the situation. I don't really need to see it. I mean, if I can, fine, but it's not super necessary. The marker is going to be looking for this explanation. This moves to the left. That answers the direction it will move. And then explain your answer. They're looking for either this argument or this argument. It doesn't matter which one you write. That's essentially what they'd be looking for in this. If you had this, you could probably get part marks, even though, like, you're not answering the question. But it's really important in these particular questions to answer the question. We're going to ask you a question. The way to get the most marks is to answer the question. I think it should go without saying, but it should be said because people often don't get the part marks that they should get because they don't answer it. So like I said, for this particular question, we told you about this in class. So essentially, I told you this part, negative charges move in the direction of increasing V. They feel a force in that direction. I told you that in class. So if you want to say that's your answer, fine. Sometimes, though, you can't remember everything I said in class, but you remember the basics. And you can put together, just like we argued in class, the consequence of these basics. So there's more than one way to do this. There's more than one way to think about answering it, but it's important to think on your feet. Circle the statement about conductors in a state of electrostatic equilibrium. I'll circle the false statement. Okay, so I guess one of these is false because I didn't write S, but you never know. Sometimes it's circle all the false statements. Let's just hunt for the false statements. If they're in electrostatic equilibrium, with these true-false questions, the easiest way to do it is just to go through and to check whether each statement is true. If it's in electrostatic equilibrium, it has no electric field inside it. That's true. Electrons in a conductor are stationary. They're not moving. That's true. That's true. That's what equilibrium means. When placed in an external electric field, the free electrons will arrange themselves, maybe rearrange themselves, in such a way that the electric field they create is equal and opposite to the external electric field inside the conductor. In other words, inside the conductor, the charges are going to move around so that the electric field they make cancels out with the external electric field. Yeah, that rings a bell. I remember answering a question like that in class. Okay. Last question. Electric field lines from external sources cannot touch a conductor. So if you have a metal conductor, do all the electric field lines go around it? The answer is no. You should be familiar in your homework with questions where we have, electric field lines. They can touch the conductor, they just don't go into it. In other words, an electric field line will come in, and then charges on the inside, is there a white pen? There is. Charges on the inside of this are going to rearrange themselves. Man, why is that so tiny? So that they cancel out the electric field, so that the electric field on the inside is equal to 0. Okay? But electric fields can touch the surface, so that is a false statement. That one's the answer. Okay? So be careful when you're doing these true or false questions. They're kind of tricky. All right. This is a long calculation question. Charge A, here it is on the diagram, has some charge on it, and it's placed at 0.11. Cool. Charge B, that's over here, has a negative charge, and it's placed at 1 minus 2. And charge C, over here, has that. Determine the force vector. Oh, man. I remember when Coach said that there was going to be a question like this on the midterm when he told us about it, but I didn't believe him. Well, maybe you should. Okay, so essentially this is a longer calculation, and I'm not spelling out all the intermediate steps because I expect you to know the intermediate steps. So essentially I say, hey, figure out what the force vector is. How do you do that? So how do we do it? Well, first we need to figure out the force vector from B on A, whatever that is. And then we need to figure out the force vector from C on A, and then we need to add them together. So, all right, from B to A. Let's start with that. RBA is equal to the position of A minus the position of B. So it's going to be 1 I hat plus 1 I hat, 1 j hat, minus 1 I hat, minus 2 j hat. So the I hats cancel out, and you get 3 j hat, which is what the vector looks like, pointing straight up. So then, the length of our BA is going to be, Pythagoras says that this has length 3, and then the unit vector, BA, is going to be times 3 j hat. Oh, good. It's just equal to j hat. Well, that's nice. Now we calculate the magnitude of the force. It's going to be QA, QB times K divided by R squared. So QA is 2.2 E minus 5. And QB is minus 3.4 E minus 5. And K is 99. And R is equal to 3. And square it. And you get minus 0.748. And so the force vector is going to be that force times R hat BA. So it's going to be minus 0.748 newtons j hat. That's part of the answer. Let's do it for the next part. Okay. RCA. C to A. That's equal to the position vector of R minus the position vector of C. So it's 1 I hat plus 1 j hat minus 4 I hat minus 5 plus 5 j hat, which is equal to minus 3 I hat minus 4 j hat, which looks about right. Cool. All right. Now we need to do the rest of this. What's the magnitude of RCA? Pythagoras says that it's 3 squared plus 4 squared all square root. So that's square root 9 plus 16, so that's square root 25. That's length 5. Hey, it's another whole number. Why is it another whole number? It's a whole number because I didn't want to write a weird bonkers. It's a whole number because I said so. 1 over 5 Rca. So that's minus 3 I hat minus 4 j hat, which is equal to Alright, I'm going to make sure I'm right here. Yay! Good. That should say j hat. Alright, the next step is figure out the force. QA QC times K over R squared. Alright, so QA is 2.2 E minus 5, and QC is 8.5 E minus 5, and 99 divided by 5 divided by 5, so that's 0.673 newtons. And then the force from CA is going to be at force times R hat CA. So it's going to be equal to like that. Okay, so the total force is just going to be these two forces added together. Force BA plus force CA. Which is, here, I'll just write it out. You don't have to do every intermediate step here. I'll address that in a second. But so then when you combine them, it's minus 0.404 I hat minus 1.29 j hat. I guess these are newtons. Newtons. That's your final answer. Okay, so before we go on, this is a pretty long question, but essentially, I mean, it's got lots of intermediate steps, but essentially, it's a super straightforward question. So this type of question, I'm asking you to show all the intermediate, well, hold on. This type of question, I'm relying on you to understand what all the intermediate steps are. You don't need to show them all. That said, before I go on, should you show them all? If you can somehow figure this out in your head, well, that's great, I guess. Congratulations. But if you do it all in your head, you probably can't. So instead, if you show these intermediate steps, you can get part marks. Okay? So let's say you did this step correctly, but this step incorrectly. You still might get 4 out of 6 or 5 out of 6, right? If you did each of these separately but forgot to add them together, maybe you would get 5 out of 6, even though your final answer is wrong. Do you see what I mean? So when these are marked, your markers are looking through not just to see if you got the overall correct answer, but to see if you understand the procedure that we use to calculate the final answer. We're looking for understanding as much as anything else. That said, before I go on, I get a lot of people complaining. Not a lot of people. I just have taught this enough times that it's happened enough that it feels like a lot to me. But I get some people complaining sometimes that they say, hey, I understood 90% of this. How come as part marks I'm getting 3 out of 10? I understand 90%. And my answer is always this. Your marker has 250 midterms to mark. They end up with really stern standards about what counts for part marks and what doesn't count for part marks. Okay? So even if you feel like you understand, and even if I believe that you understand, if you're not showing the marker essentially the work that they're looking for, you won't earn those part marks. It's like getting points in a video game. There are really specific things that they're looking for, and if you're not doing them, like we don't care how good you are playing your Overwatch character. If you're always losing matches, your rank goes down, right? Same thing here. If you're not hitting the particular points, the basic concepts that the marker's looking for, even if you feel like your understanding is almost there, you're not going to earn those part marks. So, yeah, be really specific about the stuff you show on these pages, just for your own sake. I want to see you guys get pretty good marks on this. I don't feel like this test is particularly difficult, but you know how it is. This one's a derivation, and this might be the first formal derivation we've really asked you to do since you've come to university. Derivations are kind of different than calculations, but they're very similar in nature. So for a calculation, you want your end result to be a vector or a number, okay? You followed some procedure, and that told you that the answer is this particular set of numbers, okay? A derivation works in a similar way. The deal here is that there is an answer that we want to see, or hold on. A derivation works in the following way. You do a specific calculation over and over and over, and you say to yourself, hey, every time I do this calculation, I'm following exactly the same procedure. Why can't I just jump to the last line? Why can't I just say, well, what if I follow the same procedure, but I don't specify any initial data? I leave all those unknown pieces, how much charge there is, what distance I am from the plane, all that. I leave those undefined, and then I go through the same procedure I would if I was just doing a calculation, but instead I'm ending up with an equation, a final answer equation that is in terms of a bunch of variables. And that way, if I want to calculate this specific thing in the future, I don't need to redo the whole procedure. I can just rely on this equation, okay? So a derivation is all about showing where these equations come from. So I think it's a pretty good bet that most of the derivations I could ask you for on this particular exam are Gauss's law derivations. Which talk about what the electric field looks like in a more complicated situation. And so that's what that booklet is for. The textbook has a really good description of Gauss's law. I don't care where and how you learn Gauss's law, but you really need to learn the basic ideas. And so what we're looking for here is you're going to use the basic ideas through Gauss's law to come up with this particular equation. And that involves showing each algebraic step and bringing together each argument the way you would in if you were doing a specific calculation, okay? So what you're trying to show is if somebody gave you numbers for all these cases, this is the procedure you would follow to get your final answer, a number. But instead of that, we're not specifying what those initial pieces of information are. You're following through the procedure and showing you get this equation at the end. That's what a derivation is. Derivations are super useful in physics. We saw a few kind of proto-derivations last term, but they were usually 1 or 2 steps. These Gaussian surface ones are more complicated. So are the integral-based ones. Like in class, I showed you the derivation for the electric potential around a single point charge. I decided not to put that one on this, or at least I decided to leave that out of the possibility of the derivations I might ask you for in this particular midterm, because most of you are still fairly new to doing integrals. So on the next midterm and the final exam, I might ask you some integral derivations from this part of the term, but not on this midterm, not yet, because you're still new to those mathematical techniques. Okay, so let me show you how to do this derivation. Use Gauss's law to derive the fact that an infinite flat sheet with a uniform charge density sigma will have an infinite electric field. Will have an electric field saying blah that doesn't depend on the distance from the sheet. Show every step starting with a uniform flat sheet. Okay. Show every step is kind of a complicated statement. One way to think about this is you want to justify each step you do. Sometimes there are little algebraic steps that a person kind of skips over, but we don't want to skip over any of the main logical arguments. So, without further ado, how do you do this derivation? What kind of thing are the markers looking for? Well, first, and maybe if I'm nice, I'll draw a picture of what we're talking about. We've got an infinite sheet of uniform charge. So this is covered in charge. Okay. And then sometimes it's helpful to draw it from the side. So, like I said, I might give you these drawings from the side. All right, so it looks like that. It goes on forever. But, a cross section, if I cut this in half and focus the camera right in the middle, that's what it would look like. Okay? So, step one. Define your Gaussian surface. To be box. Actually, you know what? Before we go any further, you might ask, what can we expect to be provided? Sometimes I'll draw these electric field lines. We know the electric field, according to the rules for drawing electric field line, looks like this. Maybe I need to change the wording on this question to say, draw the field lines. Give you guys a quick question. Alright, so that's what the electric field line looks like, straight up, straight down. Okay? So first, I'm going to define my Gaussian surface to be a box. The box has 4 sides, and it's the top and bottom are parallel to the sheet. Okay, so over here, the box is area A, and it cuts the sheet like a cookie cutter would. And here from the side, you see that the box is parallel to the thing. So step one is describing our Gaussian surface. Good, we're done. 2. The box contains charge how much charge will this, oh wait, hold on. The Gaussian surface to be a box, top and bottom are parallel to the sheet, area A, like I wrote there. The box contains charge. How much charge is in the box? It's going to cookie cutter its way through the sheet. It's going to cut a segment of the sheet, area A. And so in terms of the charge density, sigma, it's going to be that much charge. Next step. Gauss's law says the flux through the box will be total flux is equal to A sigma over epsilon naught. Okay. Now, 4. Let's talk about the flux through all the sides. Flux total is equal to the top hat and the bottom flux and the side flux, north side, south side, east side, west side. Okay. But we know about these fluxes. There's geometric information about the fluxes. You know that the sides of the boxes are parallel to the electric field. Are parallel to the electric field, which means there's no flux through them. North is equal to 0, south is equal to 0, east is equal to 0, west is equal to 0. What about the top and the bottom of the box? Well, in both cases, the flux is leaving the box, right? In both cases, the electric field is pointing out through the surface. So it's not that one is going to be positive and the other is going to be negative. They're going to have the same sign flux. So the electric field, so the flux is going to have the same sign, and the electric field is uniform. So it doesn't vary over the surface, so it's just going to be a constant value, and perpendicular to surface. Thus, the flux through the top is equal to the flux to the bottom. They have the same sign. And it's both, and the total flux is going to be A times the electric field strength at that location. Step 6, put it all together. Okay, so it's flux total is going to be the top, AE, plus the bottom, AE, plus the north side, plus the south side, plus the east side, plus the west side, and that's equal to sigma A over epsilon naught. 8, and we solve it for E. So 2AE is equal to sigma A over epsilon naught, which becomes E is equal to sigma A over 2A epsilon naught, which becomes sigma over 2 epsilon naught. I just proved it, which doesn't depend on the position. Doesn't depend on position or size of the box. What do you mean? Well, in some Gaussian surfaces, there are geometric terms describing the box that remain once you finish this calculation. In this case, all of the geometric terms describing the box factor out. And so you get an electric field that doesn't depend on the size or shape of the box, which means the electric field is uniform. Okay, so that's the end of that derivation. What kind of things is the marker going to look for in this type of derivation? They're going to look for a setup. Are you defining a Gaussian surface? That's what this is all about. So this question's out of 6. So if you set it up right, maybe you'll get 2. If you say that there's a Gaussian surface and nothing else, you'll probably get 1 out of 6, which is better than nothing out of 6 in terms of part marks. Arguing that there's this much charge inside the box, recognizing how much charge there is in your particular Gaussian surface, that's probably worth another one. So we're up to what, 3? Figuring out how much flux is going to be, all right, this one's probably worth 1, which is saying Gauss's law, we know the flux, we're talking about the flux now. This part is probably also worth another 1. That's 5. And then putting it all together is probably worth the 6 marks. Okay? In other words, anytime there's a derivation, you always kind of have to, all right, let's set the stage. Okay. That's 1 or 2 points, right? That's maybe 25% of the overall thing. Setting the stage properly tells us that you know what's going on. These are physical arguments. This and this, and even these two are physical arguments. They're essentially us saying, hey, we're defining the system like this. This is what we know about what's going on. That's an important part of doing any type of derivation, because derivations are all about saying, here's this general setting. We don't know what these variables are. We can make some arguments about what's happening in these settings because we know how to do this analysis. And then putting it all together finishes everything off, and that's worth another maybe 20%. Okay, so when you're doing a midterm, think strategically, and when you're preparing your midterm, think strategically. Maybe try writing out a few of the derivations yourself beforehand. I've tried to be very clear in the class which derivations I'm going to be asking you for. All right, let's start this week's homework. This week's homework is actually kind of bonkers. I mean, it's a little bit bonkers each week. I'm hoping that it will become less aggro for you guys, because there's all sorts of questions I really need you to see and try, and usually these types of questions aren't really so crazy. What do I mean by all those things? I don't want to give you the impression that I think that this material is too difficult for you, and I don't want to give you the impression that we haven't covered this material in class. It's just that, you know, this type of material makes various assumptions about your mathematical background. Like, it says, okay, what's the volume of the sphere? If the sphere has radius r, how big is it? Now, I know what it is because I was in first year, and in first year you kind of get used to these things, and second year and third year, and by the time you're a third year in physics, you know all these equations off the top of your head. But if it's a sphere, the volume is 4/3πr², and the area is πr², 4πr². Yeah. And so, like, say, if I had a total charge, Q is equal to, I don't know, 9 coulombs, uniformly distributed through the volume, what is density of charge? Well, if it's uniformly distributed, then it's volume, which is Q divided by volume. So that would be 9/4/3πr². If, on the other hand, it was uniformly distributed over the surface, the charge density would be the letter sigma, which is 9/4πr² instead of the 4/3πr³. Okay. So I know that, and Eric Mazur knows that. Arguably, the students he's teaching at Harvard know that, but I'm not sure how many first-year students can bang this stuff off the top of their heads. It's not difficult to learn, but he's just throwing you guys in, and I'm like, well, I mean, they can do it, but anyway. What I don't want you to do is get really, really discouraged with the material and just look up how to do it online. Because if you're looking up how to do it online, usually you're thinking even less than if you half-ass tried it and then quit. So for that reason, I'm going to do some of the questions on your homework today, just to show you how to do it, to walk you through the arguments. It's like I said, the material here isn't that difficult. There's just some of the missing pieces I feel like some of you might be missing out on are geometric arguments like this, where we talk about geometric distributions. It's not too tricky once you get the hang of it, but I'm not all that sure you're getting the hang of it, which is why I'm going to literally do some of the questions for you so that we can talk about what the answers are. Part of the point to these assignments is that I want you to see the various ways you can use these arguments and situations and mathematical tools. Eric Mazur is kind of working on a higher level here. So I hope that the textbook isn't like this all the way through, because overall I like the content, but these questions are just so hard. They weren't, by the way, I don't think they were too hard at the start. Some of those were pretty easy. But these ones are a little bit, I don't know. So yeah, other profs have complained to me about this textbook being a little bit bonkers at this level, and hopefully they'll even out over the course of the course. But if they don't, then I'll just keep doing this, where I show you how to do the questions, because I want you to learn how to do them. It's helpful to be able to do this type of reasoning, where you talk about volumes and densities and stuff. And yeah, so I want you to learn how to do it. I just don't think everybody knows how to do it right now, and I don't want you to get discouraged. Okay, so let's start these questions. These are pretty fun. I've written down the questions on the thing if you want to look. Is anybody? Nobody's writing in the live chat. Is anybody watching? Oh, 2 people are watching. Hey, hi. Nobody has any questions in the live chat. Okay. Well, let's begin. So, question 32 in the book goes like this. Lots of these questions are kind of basic fluxy questions, where we're sussing out kind of the little moving parts inside Gauss's law and Gaussian surfaces. So, 32 goes like this. Oh, it's a 3-ball question. What am I doing? Oh, God. I'll try it. The chapter explains that the charge inside a closed surface is proportional to the flux through that surface. Sure. To illustrate why the surface must be closed, draw an example of a charge distribution and a surface for which the flux through the surface would be considerably altered if the surface had any holes. How is that a 3-ball question? Alright. Okay, so here's our charge. I'm going to draw the electric field coming out of it too. Okay, I'm going to make this argument in 2 different ways. So first I'll draw my surface and its holes. Actually, here, let me keep drawing charged things. Okay. So how about if we have a sphere centered on the charge, but we put a hole in the sphere that they can come out of, like a vase. Okay. So in this case, all these lines coming out through the top will intersect the thing and count as flux, but these lines here will leave the surface without crossing through it and won't be counted as the flux. This question is so weird. So let's do a cross-sectional cut of this diagram. It's kind of hard to see in 3D. So here's what the electric field looks like for our single charge. And it's a cross-section. Cool. And here's what the cross-section of our jar looks like. Yeah, look at all these red lines. They're not getting counted as flux. It's a pretty simple question, I think. I don't know. Maybe I'm answering it wrong. The chapter explains that the charge inside a closed surface is proportional to the flux through that surface. To illustrate why the surface must be closed, draw an example of a charge distribution and a surface for which the charge flux through the surface would be considerably altered if the surface had any holes. Yeah, okay. I mean, I guess I did that, right? If you punch a hole in the sphere, the lines can come through. All right. 35. When a charged particle is placed at the center of a spherical Gaussian surface, now we're talking. The field lines through the surface is plus phi. Phi is the symbol we use for flux, because Greek phi is the letter is the sound f for flux. Suppose the spherical Gaussian surface is to be replaced by a cubical Gaussian surface composed of 6 square plates. Square plates are positioned above below the charged particle to form two sides. Hold on. Square plates are positioned above and below the charged particle to form two sides of the cubical Gaussian surface that is centered of the charged particle. What are the field lines through each plate? This is a great question. Alright, so let's start just by drawing a sphere. This particular question is trying to buffalo you with details. Alright, so I'm going to start this question by drawing three-dimensional figures. And you're going to say, wow, that's crummy art. And I'm going to say, hey man, whatever. So if you do it for a sphere, there's a flux going through the sphere, and the total is equal to phi. Right? Not minus phi, phi. Plus phi. Cool. All those lines are going out. You count them out. There are 1, 2, 3, 4, 5, 6, 7 lines coming out. If instead I used a big box, cool. What would the flux through the box be? It'd be exactly the same. All these lines would leave through this box. Fine. Okay? So the flux through the green box is the same amount of flux. Cool. Here's the thing. This is a very symmetric situation. I'm going to draw it from the side here so we can talk about it a little bit easier, so I can make my point a little bit easier. Here are my electric field lines. Okay, cool. So we're talking about a rectangle, a square, sorry, centered on the axis. Like that. Okay. Calculating the flux through each of these sides is actually a tricky business. It's tricky for two reasons. One is that the orientation of the electric field changes over the course of the surface. So here it's perpendicular, and out here it's less perpendicular. And also it's tricky because the strength of the field changes. So over here the strength is stronger because it's closer to the charge, and over here the strength is weaker. So calculating it outright is actually a pretty difficult game. But that doesn't mean we're useless. Because let's think about it. This is a symmetric setup. What's the flux through each of the sides of this box? The flux through each side is equal to the overall flux divided by 6, because there are 6 sides. Right? So the flux through the top plate is going to be total phi over 6. The flux through the bottom plate down here is going to be big phi over 6. So the flux from the two plates together Why is that tricky? Well, it's tricky because, you know, you spend the first part of the chapter talking about flux, and there's that cosine, and sometimes we do integrals, and it's super gross. But then what it does is it comes down to us saying, well, let's use symmetry instead. We know what the overall flux is. We know that the sides are essentially the same. this side has the same flux going through it as this side does, and that has the same flux going through as that side, because it's a square, it's a cube centered on the midpoint. So even though you can't calculate the flux using the electric field, you can still calculate the flux using symmetry. So yeah, that's fun, right? I had fun. Let's do question 36. Oh, fun. Figure blah shows a cross-section through an infinitely long, uniformly charged hollow cylinder. How does the magnitude of the electric field vary with radial distance from the cylinder's long central axis inside the hole and outside the hole? Okay, let's just draw a cylinder. Hold on. This is what a cylinder looks like. It's a tube. Okay? And it goes on forever. Okay? So, what they're telling you in this question is, we're going to put charge on this tube. This charge is going to be covered in tube all the way around. What kind of electric field is it going to make? How strong will that electric field be? It's a tricky question to answer. Part of the reason it's tricky to answer is because looking at things in 3 dimensions is actually bonkers difficult. You know, it's just like, what's the, what does that drawing mean? So to clarify things, instead of drawing the system in this way, what we do is we look at it from a cross section. In other words, we're going to imagine cutting a chunk of it and looking at the field and everything on this plane. And that's the drawing you see in the book, which looks like this. Plus, 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 plus. So, what does the electric field from this thing look like? Well, we know that it's infinite. Do you remember in class when we were talking about the infinite field from the field of an infinitely long flat sheet of charge? And I was arguing to you that the electric field would have to behave in a certain way. It would have to be uniform and all pointing away from it, because there's no room for an electric field to tip over to the left or right. You can use a similar argument on this particular field, where you can say, hey, all of the field lines coming off this side of it have to be parallel to each other. Why do they have to be parallel? They have to be parallel to each other because there's no room for one of these to tip over without crossing one of its friends. And that goes all the way down the pipe. So they all have to be parallel to each other. Fine. How do we draw the electric field lines for these? Well, imagine them as point charge. That tends to work. All right, hooray! You just follow the field lines. These guys are all spreading out in the horizontal plane, right? Splaying out. What about on the inside here? What do these field lines do? What do the field lines inside the tube do? They can't go up and they can't go down because there's already a lot of field lines there. So they gotta maybe point in towards the middle? Huh. As it stands, this is a geometrical argument, by the way. There's a similar calculus argument that you can use that just says that in the inside of a sphere or a circle like this of uniform charge, there's no field. But you can see that in terms of just drawing the art, there's no way for these lines to go inwards at this point without crossing. Because either the lines are going to cross or they're going to end. So they can't cross, they have to end. If they end, they have to end at a charge. There's no charge inside there. So as a result, in this case, there's no electric field in the middle. We're going to talk about some more complicated cases in a little bit where there are charges inside these hollow bits. But generally speaking, anytime you have a sphere or a ring of charge like this, the electric field inside this region from the ring of charges is 0. If you have other charges inside here, the electric field might not be 0, but the electric field from the blue ring of charges inside the ring is going to be 0. So this is what the electric field looks like. Alright, so what was the question? The question was, how does the electric field vary with radial distance from the central's long axis? Okay, so the axis is running down the middle of this, right? In this diagram, the axis exists as a dot in the middle. So we want to know how strong the electric field is as it depends on distance. And the way to do that is to imagine Gaussian surfaces inside there or outside there. So let's do the inside one when r is less than the radius cylinder. Our Gaussian surface is the one I just drew here in green. How much charge is inside of it? 0. So what's the total flux through it? 0. The flux through the top plate is always going to be 0. The flux through the bottom plate is always going to be 0. In these cases, because of symmetry, there's only going to flux through the side part of the plate. So we see in this diagram that the flux through this ring is 0. So the electric field inside is going to be 0. When the radius is larger than the ring, than the cylinder, let me clean this up a little bit. Boop, 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 boop. When the radius from the ring is larger than the cylinder, like there, it's from the cross section that looks like this. How much charge is inside of it? Well, the charge is going to depend on the linear charge distribution of the cylinder, right? And so the charge enclosed, so by the enclosed charge, you imagine this is literally a box, and so it has snipped off this length L piece of box. L lambda is the amount of charge inside there. And then so the area, flux through the top plate, flux through the bottom plate, flux through the side plate, will all add up to L lambda over epsilon naught. So we know that the flux to the top plate is going to be 0. The flux to the bottom plate is going to be 0 because they're parallel to the field, right? The field's running horizontally, and this top and bottom, right? This top plate and this bottom plate are also horizontal. And so the entire side, that's going to be area of the side times the electric field strength. L lambda over epsilon naught. So what's the area of a cylinder? Radius r. Do you know how to calculate the area of the cylinder? Eric Mazur assumes you know how to calculate the area of a cylinder. The trick to calculating the area of the cylinder is, it's really fun. You're going to learn how to do it in calculus probably. You imagine you have some scissors, and you're going to cut along this line and unroll it. If you unroll it, you end up with a roll. The height of that rectangle is L. How long is this part? Well, it's the distance around the circle. So it's the circumference of the circle, 2 pi r. So the area is equal to 2 pi r times L. So the electric field is going to be L lambda over epsilon naught times 2 pi r times L. These cancel out. Lambda over epsilon naught 2 pi r. And you see here that it was asking about how the electric field varies with the distance from the middle, it varies with the distance from the middle like 1 over r. Once you're outside, inside the electric field is 0. So that's the answer to the question. All right, let's see if anybody has any questies on the live chat. Nobody has questies on the live chat. Poor things. After we get through this midterm, life is going to be so cool. You're going to see me using all these theorems that we've been talking about to talk about electronics. And then you're going to be like, wow, I never knew how electronics worked. And I'm going to say, we derived all these properties of electronics from basic ideas. And you'll say, wow, I never knew that all these complicated things came down to such basic ideas. And I'll say, I know, that's what this course promises you. But right now, you're right in the thick of learning the theory. It's almost, the theory part is almost done. We're going to get to the fun part soon. Okay, so the next part is called charged sphere with a cavity. Oh, hold on. I copied down the name. This one isn't in the textbook. I was copying this off the assignment, but so I don't know where it is in the textbook. So I'm having trouble with the words. Let's I'm gonna open up Mastering Physics and read you the question directly because the way I've got it written is bad. Mastering Physics. Assignments. Oh, come on, you're so slow. Charged sphere with a cavity. Let's go. All right, some from the question itself. It says an insulating sphere of radius a, centered at the origin, has a uniform volume charge density rho. And then part A says, find the electric field inside the sphere in terms of the position vector r. What do we mean by insulating sphere? Why did we specify? Why did we specify that this was an insulating sphere? It's an insulating sphere because what we mean is, you know, assume it's like made out of styrofoam or something. We can deposit electrons in the sphere with a certain distribution. So a uniform charge distribution means that it's distributed throughout uniformly. It's kind of like mass. You know, you've talked about mass density before, where it's like there's a brick of cheese that is 1 kilogram per cubic centimeter. And then they're like, if I take 4 cubic centimeters of cheese, what's its weight? In a similar way, we're describing charge. Somebody gives us a charge density, and you multiply that by the volume to figure out how much charge there is in total. So we want to figure out what the electric field is. I'm going to draw a picture of it, okay? At this point in time, you guys are like, enough with the pictures already. And I'm like, no, pictures are great. I love drawing them. Okay, so it's got a uniform charge density, which means there's charges everywhere inside this uniformly distributed on it. Okay. calculating the electric field in this circumstance is actually a little bit tricky, but it's super fun, and we use Gaussian surfaces to do it. So what shape Gaussian surface are we going to use? If you haven't clued in, I think I told you explicitly several times in the Gaussian surface booklet that you were supposed to have done. But Gaussian surfaces, Gaussian boxes always reflect the symmetry of your system. So if this is a spherically symmetric system, we're going to, then the electric field will be spherically symmetric, and we can choose spherically symmetric Gaussian surfaces. So in this case, we're going to choose a Gaussian surface that's a sphere inside of our sphere. Radius capital R. Okay. So this game is the same as it's always been. The electric field is going to be perpendicular to the surface. So the total flux here for a sphere is going to be the strength of the electric field times the area of a sphere. Electric field times 4 pi r squared. Remember what I said there at the start about Mazur assuming that you'd mastered all these sphere and cylinder equations? Yeah, that's what I'm talking about. It's like, what's the area of a sphere? You gotta know. That said, you get a cheat sheet on your midterm, so just jot the equations down and know how to use them. So, the total flux is equal to the enclosed charge divided by epsilon naught. Here's the fun bit. What's the enclosed charge? The enclosed charge depends on how big our little green sphere is. If it's small, it's not eating very much of the charge. If it's really big, it's got a lot of the charge in it, right? So the enclosed charge is the volume of a sphere times rho. And the volume of the sphere is 4 over 3 pi r cubed, as you will learn in your calculus class, which you are just taking now. So what we said is E times 4 pi r squared is equal to 4 over 3 pi r cubed rho over epsilon naught, which becomes E is equal to 4 pi r squared epsilon naught. Let's play the cancellation game. I never get to play it because people are pretty bad at it, but boop, boop. All right. So this becomes rho times r is equal to 3 epsilon naught. That's fun, right? Okay. Before I go on, we need to talk about how to answer this question in the thing, because to add a little bit of difficulty, it's asking for the electric field vector, okay? And here we have the magnitude of the electric field. And for the most part, I just kind of care about you calculating the magnitude of the electric field. How are you going to calculate the electric field vector? Well, what direction is this electric field pointing? It's going to be pointing outward, right? That direction in a sphere is called r hat. Which, all right, here, let's talk about a sphere. A sphere. All the locations on the sphere can be described in terms of a position vector, r, which goes from the middle to the sphere, right? So the magnitude of r is the radius of the sphere. Yeah. And so r hat is going to be 1 over, wait, that's the magnitude. 1 over r, oh, come on, be nice. 1 over the radius times our original r vector. And so, if you plug this into the equation, the electric field strength is going to be rho times r over 3 epsilon naught r hat. And because they hate you, you write it like this. 1 over r vector cancel, cancel. E is equal to rho over 3 epsilon naught r vector. Yeah? So hooray, things are more complicated and stupid than they need to be. I'm going to enter this into my equation and see if I got it right. So it's rho, right, rho. Oh, no, not rho twice. Okay, rho over 3 times gosh, mastering physics times, where's epsilon naught on this thing? Special keyboard? Oh, what's going on? I don't see why they can't just teach it, make you typeset everything in. R. Submit. What? What's the right answer? Oh, cancel. Do you not write your times things in that? What's that? What kind of nonsense is this? Tell me what the answer is. Hey, that's what I wrote. What? Oh my god. Shut up. Alright, hold on. Mastering Physics wants the R vector in the top here. If you don't write it in the top, it'll lose its crap. You know what? I'm canceling this question from the tutorial. That has made me too angry. It's a good question, but come on. Come on. First you assume people know geometry. God. Alright, hold on. Stupid question. Alright. There. Now I feel better. Well, good question, but honestly, can you imagine? Cripes. Alright, what's question 43? 43. The two-cavity metal object in figure 2.4 is electrically neutral, but each cavity contains a charged particle as shown. What are the charges on the surface of each cavity and the charge on the outer surface of the object? Oh, I love this question. You ready? How do you do these? I mean, you could read the textbook, but... Okay, so how does it start? It starts by initially you put them in there and the electric field's like, hey, this is what we look like. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Alright, so there's 5 lines per charge. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Cool. Okay. And then the metal, which is, I mean, this stuff, that's the metal. The metal's like, oh, hey, we see electric fields. We're going to move all our electrons in a way that cancels these electric fields out. Okay? So, it's going to move some charges here. 1, 2, 3, 4, 5, I guess. To cancel out the electric field from the positive one. And it's going to move some charges here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, let's start with that. Moving those charges there is going to cancel out the electric field inside of the meat of the metal. And now the electric field looks like this. And this one looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're not done. And the reason we're not done yet is that all this charge and all this charge came from somewhere. They had partners that they left behind somewhere else in the metal. Okay? So once the metal's done this, it treats all the rest of the charge, so there's still, I mean, if you pair them off, oops, didn't mean to do that one. If I were to pair them off and say, well, this one corresponds to that one, 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 this one corresponds to this one, there'd still be 1, 2, 3, 4, 5 negative charges remaining. Where would those be? Those are going to go to the surface, the outer surface, because they essentially hate each other. So there's going to be 5 negative charges on the outer surface. 1, 2, 3, 4, 5. These are going to make their own field lines that don't penetrate into the thing, because otherwise if it did, it wouldn't be electrostatic equilibrium. And now we can talk about total charge. Okay. There's 2 ways to go about doing it. One way is to use Gaussian surfaces and to say, okay, what's the flux through that surface? Well, the electric field everywhere on that surface is 0 because it's electrostatic equilibrium. So the total charge there must be 0. And so in terms of this question, there was plus Q on the inside, so there must be minus Q on the surface. Okay. Same thing with this one. You can draw a Gaussian box around that one and say, what's the total flux? You know the electric field everywhere in there is 0. So you can say, oh, well, the total electric field all over is 0, so the flux is 0. So that means the total charge inside must be 0. There is minus 2Q charge on the inside here, so there has to be plus 2Q charge on the surface. And because the overall metal is electrically neutral, that means on the outer surface there has to be minus Q worth of charge. Does that make sense? There's another way to do this, and the other way is super fun. Okay? So, ready? One of the ways is to say, hey, I know that there's charge on this surface, and I know there's charge on this surface, and I know there's charge on this outer surface, right? The outer skin, the inner skins and the outer skins. It's like a peach. Gaussian, ooh no! Gaussian pillbox. What you can do is you can say, okay, well, how much flux is there through this thing? Well, the flux must depend on the total amount of charge, which is an electrically neutral thing, which has 0 charge, and then there's the charge inside this, which is plus Q, and the charge inside this, which is minus 2Q, right? And so the overall charge in this box is minus Q. And then you can say, oh, well, you know, you can account for this much and this much and this much and this much, and those all cancel out. And so the charge on this outer surface must be minus q. So that's one way to do it. But like I said, there's a more fun way to do it. And that way is counting field lines. Field lines are such a useful tool, even though, you know, it's essentially just doodling. How many field lines for charge? There's 5 field lines per Q, right? So this one has 10 field lines. And then you think about these surfaces as like kind of things of charge. How many lines go into this surface and disappear? 5 lines go into the surface and disappear, so there must be minus Q worth of charge. How many lines go into this surface and disappear? Well, 10 lines come out of that surface and then disappear. They end at that surface. So that surface must have plus 2Q. How many lines start at this surface? 5 lines start at that surface, or end at that surface, so minus Q worth of charge on that surface. You see? The neat thing about Gauss's law and then these drawings is, and then conservation of charge, is that they all kind of amount to the same ideas, just seen from different angles. It's pretty fun. Question 49. Figure 2.4 shows a neutrally charged block with 4 hollow chambers inside. Charge minus 5Q is collected on the outer surface of the block. Inside the 3 chambers are particles that carry charges plus Q minus 2Q. Determine charge inside the 4th chamber in terms of Q. So here's what you look like. Minus. So this has plus 2Q in it, and this has plus Q, and this has plus Q. And the question is, how much are on this one? And you know that this block is neutrally charged. Oh, that's such a great question. Okay, so you know that minus 5Q has accumulated on the outside. So this total is minus 5Q. You also know, based on what we talked about in the last one, that charge is going to accumulate around each of these. It's going to accumulate to cancel out the electric fields. How much charge is accumulated on each of these? There has to be minus Q worth of charge on this top one. There has to be minus Q charge on this one. There has to be minus 2Q charge on that one. So, what's going on here? Based on conservation of charge, you know that all of these different surfaces have a total of minus Q, minus 2Q, minus 5Q. So that's 1, 2, 3, 4, minus 9Q worth of charges on all the other surfaces. So for conservation of charge sake, all of their spouses must be lined up here. So that must have plus 5Q worth of charge on the outside of it, which means inside of it, it must have minus 5Q worth of charge. Wait, what am I saying? Hold on. You know that this thing has plus 9Q worth of charge on the outside. So the inside must have minus 9Q. Yeah? And that makes a lot of sense because in the end on these things, the amount of charge on the outer skin of your box, here, maybe I'll use a different pen. The amount of charge collected on the outer skin of your box, of your neutrally charged box that's full of other charges, is always the sum of all of these other ones, right? So that's a fun question. Now it's time for 82. All right, hold on. Let's see if there's anybody asking questions in the... No, nobody's asking questions. Cool. All right, on 82. This shows the cross-section through a system that consists of an infinitely long charged rod centered in a thick cylindrical shell. The shell is made of conducting material. The rod is made of a non-conducting material that has uniform linear charge density. The electric field associated with the system is indicated by the field lines of the diagram. Yeah, that looks right. Wait, what? For each finite length L surface of the system, there's a charge minus Q on the shell's inner surface. For the same length, determine the charge on the rod and the shell on the outer surface. In terms of length L, what is the charge on the shell? What's the ratio of the surface charge density on the shell's inner surface to the surface charge density on the outer surface? All right, this question's fun. So before we go on, you got a pipe. Oh, come on. Draw it nice for once. You have a pipe, and it's infinitely long. Okay? And it's also a thick pipe. Okay. Down the middle of this thick pipe is this rod. Okay. And both are probably charged. So this rod's generating an electric field and the pipe's made of metal. And there's a trick. The trick is, nowhere in this question do they specify that the pipe doesn't have electric charge. That's going to come up. In the last two examples where we were doing those boxes with cavities, they were neutral conductors. This one doesn't necessarily need to be a neutral conductor. I'll talk about that in a second. So the reason I'm focusing on that is the diagram that I drew looks like this. Okay, so this one is length R, and this one is length 2R. And the electric field they drew looks like this. And then one, two, three, four. Okay, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. Get out of here, 9Q. Okay, so there's two tricks here that really triggered my alarm when I looked at it. The first is that the number of lines on the outside here isn't the number of lines on the inside. What does that tell you? That tells you that the number of charges creating this electric field is different than the number of charges creating this electric field. So that's one aspect to it. There's another even bigger clue that that's the case, and that's that these outer lines are pointing towards our pipe, whereas these ones are pointing towards the pipe too. In other words, if the pipe was neutrally charged, these would be pointing outwards. They're pointed inwards, so something more complicated is going on here. Okay, so how do you crack this question? This is a pretty fun question. We know this is a conductor. So you can assume that there's negative charges here on the inner surface, and then positive charges, wait, hold on. I guess negative charges on the outer surface too, huh? Negative charges? Question mark? That's what it looks like. So we're talking about two different lines of charge. One way to think about this, in a way that may make a little bit more sense to you, is in terms of there being 3 pipes instead of 1 thick pipe and 1 rod. So there's the inner rod, that's this one, and then there's the middle pipe that's covered in charge, and then there's the outer pipe that's covered in charge. Okay, it might be helpful for us to think of these three different surfaces instead of 2 objects. The electric field is indicated by the field lines. For each finite length L of the system, what are they talking about there? They're saying, okay, let's imagine we got a chunk that looks like that. Just snip it. Gives you a ring here. Snip. Gives you a ring here. And snip. Okay, that's what they're talking about. For each finite length L of the system, the charge minus Q on the inner surface. Okay. So, in terms of the intermediate pipe, what we're saying is if you cut a chunk length L out, it will have charge Q on it. Which means that the linear charge density, or minus Q, sorry. The linear charge density is minus Q over L. That's fun. For the same length L, determine the charge on the rod. Okay, so the rod's got to have an equal amount of linear charge density because all these charges here cancel out the electric field lines from there. Same number of charges, right? So for the rod, lambda is equal to plus Q over L. Okay. Wow. So this is super fun. This is super fun because we need to literally count the field lines to answer the rest of this question. There's no other way to know how much charge is on the outside here than to look at the ratio. Let me just make sure I counted my diagram here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Woo! 1, 2, 3, 4, 5, 6, 7, 8. All right, 8, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, yep, it's the same. The ratio is the same. The drawing's not exactly the same. If you were confused, you can look at the book. I just didn't want to draw that many lines because I'm not as good an artist. So the inside part, there are 8 lines coming into this, right? 1, 2, 3, 4, 5, 6, 7, 8. 8 lines means Q over L. Okay, that's the ratio of charge per how about if we just say 8 lines is equal to Q? Okay. On the outside then, there are 6 lines. Okay. So Q out. How much charge is there on the outside? Well, 1 line is equal to Q over 8, right? So 6 lines is equal to 6 times little q over 8, which is 3 over 4 little q, and that's q out. So there's lambda outside is equal to 3 over 4 times lambda inside. We determine that ratio just by looking at the number of charges, counting the number of lines. Okay. In length L, what's the charge on the shell? Okay, so that's question C. In length L, there is little q on the inside, minus little q on the inside, and there's minus big Q on the outside. So the total is minus q minus 3 over 4q. So that's minus 7 over 4q. There's this much charge per unit length on the shell, on the pipe in its entirety. What's the ratio of surface charge density on the shell's inner surface to the shell's outer surface? Oh, before we go, that's not neutrally charged, right? So that's neat. Okay, so D, it's asking for surface charge density, which is the charge divided by the area of the surface. Okay, so for the inner one, the area is equal to the circumference. It's equal to the length of the pipe times blanked out there. Times the circumference, 2 pi r, right? So the inner surface has a total charge little q over L times 2 pi r. Lambda for the outer one, the radius is twice as big, so it's q out over 2 times 2 pi 2r. Q out is minus 7, nope, not 7 over 4. I guess we got that one. Minus 3 over 4q over L times 2 pi times 2r. And then it wants the ratio inner surface divided by outer surface. Gross. Minus q over L times 2 pi big R divided by minus 3 over 4 little q divided by L times 2 pi times 2r. Cancel, 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 cancel. So the answer is going to be 8 over 3. Oh boy, that's satisfying. All right, that's 82. Time to do question 76. Two parallel vertical sheets, vertical, of infinite extent carry a surplus charge and are 50 millimeters apart. Okay. So what does this look like? This looks like there's one sheet like that, and another sheet like that, and they're infinitely long, and they've got charge all over them. These infinite sheet ones, if you haven't noticed, my tendency is to draw pictures using side views. Okay. So in the first question, they're both like that. What's the electric field going to look like? I don't know. How about maybe like that? Maybe like this? Maybe this goes like that? I don't know. Weird. We know what the shape of the electric field though is, right? You know that it's going to be all straight lines. But the idea here is over here E1, over here E2, and over here E3. And given the charge distributions on each of these, we need to figure out how strong those electric fields are. It's actually a lot more fun than it looks. Where to go? 76. There you go. 0.3 nanocoulomb per meter squared. Okay. So how do you do these questions? It's really fun. What you do is you draw a couple boxes. So you got one box here. I'll call this box A. And then you got another box, say, where do you want to put it? Maybe with both of them in it? How about that, huh? I'll call that box B. Or how about if I call this first one box C? Just because we're going to talk about areas in a second. Okay. So whatever you want, whatever floats your boat in terms of these boxes, just go bonkers. You have to draw two of them. One of them straddling one and the other straddling the other, or one of them straddling both. It doesn't matter. Because we're going to reduce this down to an algebraic problem. Okay. For box C, the charge enclosed is going to be charge phi. The charge enclosed is going to be 3 nanocoulombs per meter squared times the area of the box divided by epsilon naught. Yeah? All the flux is going through the left side and the right side of the box, right? In the previous case, last time I did an infinite sheet, it was the same amount on both sides. But in this case, we don't know if it's the same amount on both sides because you don't know what the electric field strength is in the middle. So you go, the first one is on the left-hand side. It's E1A. And on the right-hand side, it's E2A. That's what's going to, the flux is going to be. I mean, I guess in this drawing, you got to be true to your drawing, right? So in this drawing, the flux was going into the box. So I should probably call this minus E2A. It's important to be responsible. Essentially what you do is you just go by your drawing. And then in the end, if you get a negative sign, it just means that your drawing had the wrong direction. So in this drawing, I assume that it was pointing to the left. It might be pointing to the right. It might be 0. I don't know. Okay. And then you simplify these equations. E1 minus E2. Essentially, I'm dividing both sides by A. 3 nanocoulombs over epsilon naught. Cool. Now for box B. The flux is going to have, well, the total charge enclosed is going to be 6 nanocoulombs per meter squared times A over epsilon naught. The flux going through the left-hand side is E1A, and the flux going through the right-hand side is plus E3A, because they're both going out in this diagram. And so this guy becomes E1 plus E3 is equal to 6 nanocoulombs per epsilon naught. All right. We have 3 equations and 2 unknowns. Do I need to define the third one? Yeah, maybe I have to define a third box. Call that box D. So in box D, let's get these fluxes right. The flux is plus E2A plus E3A. Oh, no, that works out to the same. Good. We're fine. So, now what? Now what? It's been a while. You go... let's see. Because of symmetry, I think E3 should equal E1. E3 is equal to E1. Because the field strength is just going to be a superposition of the 2 individual fields. And then... yeah, the field strength is just going to be a superposition of the field from this one plus the field from this one. So over here it should have the same strength as over here. And oops. So you put those together and you end up with E1 is equal to 6 nanocoulombs over epsilon naught divided by 2, so that's 3 nanocoulombs divided by epsilon naught. And then you put it into this expression, and that becomes 3 nanocoulombs over epsilon naught minus E2 is equal to 3 nanocoulombs over epsilon naught. So E2 must equal 0. So in this case, there's no field in the middle here. Who knew? Yeah, that was a fun thing. All right, part B. So in part B, this one has plus 3, and this one has minus 3 coulombs. What does the field look like? I don't know. Maybe out like that, maybe? Maybe like that? Maybe like that? So I'll call this E1, E2, E3. And again, I'm going to set up two Gaussian surfaces. One like that. I'll call that one B. And one like that. I'll call this one C. Okay. So, alright, so flux, charge enclosed. So, for box B, the total flux is going to be A times E1 plus A times E2 plus, because in our drawing the electric field lines are going to the leaving the box on both sides, and the flux is 3 nanocoulombs times A over epsilon naught. So E1 plus E2 is equal to 3 nanocoulombs over epsilon naught. Cool. For box C, it should be AE1 plus, because it's leaving on the left-hand side, minus AE3. It's minus because it's going in on the right-hand side. And that's equal, and the total charge enclosed is 0. Hooray! That's weird. So as a result, E1 is equal to E3. Oh wait, hold on. Minus that. And okay, so now we need to talk about adding the electric fields together, because you know from symmetry that E1 is going to have the same field strength as E3 does. Maybe the opposite sign, because we're on the opposite side of this plus minus thing, but it's probably going to be, so E1 plus E3. Oh wait, hold on. Like this, minus E3. And the result is that when you plug this into this equation, you get 2AE1 is equal to 0. And so electric field 1, 3 is 0. And, oh no, what? Okay, and then as a result, the electric field between them is equal to 3 NC over epsilon naught. Hooray! That's kind of fun. You know, I don't know if doing it with Gaussian surfaces is the funnest thing to do. I think maybe just using the superposition principle is more fun in this case. Yeah, you can use the Gaussian surfaces to calculate for one sheet, and then add them together. We're going to see a situation like this in class. Capacitors, I'll probably do it with electric field strengths instead of Gaussian surfaces, just because Gaussian surfaces become really weird. Alright, 62. Let's go, one more. 3 particles, each carrying charge plus Q, are located on the quarters of an equilateral triangle side A, length A. Cool. Triangle centered at the origin. Hello, I'm the origin of the Cartesian coordinate system. What's the electric flux through a spherical Gaussian surface centered at the origin if the radius is a over 4 or 2a? Alright, so a over 4, that's... So if the radius of our first one is a over 4, then the diameter is half the area. And so it's not going to hold any of them in it. I don't think. Let's just check that first one. So if you have a triangle here, this is a over 2, and this is a, and it's an equilateral triangle. What's the height to the center? So that is okay, equilateral triangle. These are all 60 degrees. So that means this one's 30 degrees, and this one's so 30. Yeah, hold on. So then this length here is 10 of 30, 5, so that's 0.2886 a times 0.2866, so we'll square that, plus 4, square root answer. All right. So just to dot our I's and cross our T's, the distance from the middle of all these corners of the equilateral triangle is a times 0.577. So our first sphere is definitely enclosed. Holds no charge. So the electric flux for the one in part A is equal to 0 because it's got no charge in it. And for part B, 2A, it holds all the charge. So the flux through that sphere, the big sphere holding all of them, is going to be 3Q over epsilon naught. Alright, well that's it for this week's online office hours. Good luck with these questions. They're pretty fun once you get the hang of it, but it takes a while to get a hang of it, so don't sell yourself short. Give it a go. Talk to you later.